Oh, yo, yo, what's up, what's up? Welcome back. Today we're working on my image to text neural network. So the idea is that I kind of want to be able to like textify a arbitrary picture, right? So turn it into like ASCII art. So we might have like this picture of like a landscape, and maybe we want it to be rendered in the terminal, or just for fun, like maybe you want to like copy paste some shitty image into like a message with your friends. And so it's kind of nice to be able to like, well, nice. There's no reason to do this for real, right? But it's kind of like a fun project to say like, well, can we render this with text? And sorry, yesterday we implemented this like super naive approach where we have like characters that represent brightness values, I guess. So like, you know, the @ symbol takes up a lot more pixels within a glyph area than an empty space does, right? And so we're kind of saying like, well, as we like move up these characters, we have like more pixels wide. And then we essentially like sampled some area of the image, like 12 pixels by whatever the aspect ratio of the character is. And we said, okay, we'll just pick which character based off of how bright that is. And that's like, looks okay. But I suspect that we can do a lot better, right? Like you can imagine that if you have like a 5x5 grid of pixels, say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And if you were to like fill in these ones, like these ones were the bright ones, right? You'd be like, oh, certainly a capital X fits this very well, right? But like we don't have any idea in our naive implementation of like locality of where the brightness is. And so what I was thinking is, well, you could like probably figure that out, right? Like say you were like rendered every single character and then you compared it to like this grid and then you said like, oh, one of these matches that the best. But that's like pretty inefficient, right? If you wanted to like figure out the best, if you want to do that for every single area of an image, you'd have to run through every single character for every single image or come up with like some intelligent hash map, right? You could maybe say that like we'll pre-compute all of the different pixel grids and map them to specific characters. But then you look at this and you say like, well, say that there's like 255 pixel values for each of these, but like let's say we like quantize that down to like maybe like 8 or 4 or something. You'd have however many you quantize down to, is like 4 to the power of like 5 times 5 to the power of 25 options. That's a lot of things to pre-compute, right? And so the idea is maybe we can take a neural network and have it kind of learn about what matches well, and you could probably get like a pretty good approximation of like the perfect version in a lot less space, right? Because like the neural network, you can kind of think of it as like compressing down information into like other formats, and using that to like extrapolate essentially. So that's what I want to try. We haven't done any like neural network stuff yet, so that's what I want to work on today. I'm going to work in Pytorch just because it's what I've worked in before. I think that like there's other neural network frameworks out there. I've heard of TensorFlow, which I would like to try at some point, but I haven't got there. Pytorch is just the one I'm most familiar with. So I think I imagine that they're all similar enough, but like maybe tooling around them is probably kind of different. Maybe syntax is different. I'm not really sure. So I think probably what I want to do is I want to start by doing like some sort of like Python or Pytorch hello world, like kind of just build up the concepts of like what does it take to train a neural network. Then we're gonna have to try to like figure out what is like a good input, like what do we want our inputs and outputs to be for this scenario, right? Like we have this image, we have characters, like do we want to process a whole image at a time? Do we want to process one character at a time? Like how big are the characters going to be? Do we need to like normalize our inputs in any way, right? So we're going to have to like define our inputs and outputs. We kind of came up with like this really shitty loss metric yesterday. So like for like how good our matches, we last time we just like subtracted one from the other. So we said like we put all of our text in there and we subtracted it from the real picture. And you can see that like the difference is almost entirely the whole picture. So I think that we want to experiment with like if we get a neural network training, is this metric valuable? Does this metric trend us towards something good, or do we need to like come up with like a better metric for like what is good? So we'll have to find like loss or what is good. And yeah, I think that we'll just kind of go from there, and we'll see. I'm sure that we might not even get to the end of this because we might like rabbit hole down something along the way. So I think probably let's just get moving and see what happens. So that's like maybe 5:20 in. We've done our intro. How does it decide which care to use? So right now we just basically figure out how bright each area is. But the neural network will do something different, and so we'll have to figure that out when we get there. So let's do like a baby's first AI. So let's just make up like a little train script that uses Python 3, and we're gonna have to do our little if name is equal to main. We run our main function, and are we gonna have any arguments passed in? Right now, probably not. So we can just say like main like this, and let's like just look up. Here I Googled Pytorch train neural network, and I clicked a couple of these. It doesn't really matter. I've got like kind of like a good idea of what's going on here, and probably it's worth breaking this down a little bit. So there's this really good video by Sebastian Lag, YouTube. Let's see. It's like Sebastian Lag neural networks. And this video is like, where'd it go? I swear it's this one, how to create a neural network. This is like a really, really good video and like really breaks down like exactly what's going on there. So I suggest like if you're getting into neural networks, this is like a really good place to start. But essentially, a neural network is a series of like inputs. You know, you have like, let's just start with something simple. Say you have like a function of x, right? And you could say like, what if you wanted to draw a line? You might have like a function x that's equal to like mx plus b, simple line formula, right? Essentially, a neural network is a lot of these guys. So each input, you might have like many inputs, but you will like stack up your inputs with like these like linear functions with like a little bit of extra processing. So you might have like, I guess at its core, you have like neural network is function of n parameters and its output is m parameters, right? And so you have like these nodes that you might like, you can think of them as nodes. People like draw them as graphs often, but like say I wanted to like model a linear function. Well, I have like these like nodes that can do mx plus b, each of these guys. So each of them will have like an input multiplier as well as like an offset. And so I'll have like my input, which is like, say I have like a number 2. I put the number 2 in. He goes into this guy and he's multiplied by like weight m and then added to bias b, and that's the output. And so if you wanted to like do something more complex, you might have like multiple inputs, and they might be connected to like multiple nodes, and they might like even these guys then might be connected to more nodes over here. And if these guys all with like a lot of connections and a lot of like processing, you might end up with like complex behavior out of this like very simple idea. The only other core piece of information that you need is if you imagine these guys as all like linear, how do I say this? If you were to imagine like multiple linear functions and you just like add them up together, you might have like, you know, some function like this and like some function like this. And if you added these two guys up, you would just get like a flat line, which might not be what you want, right? You might want like some sort of, you're trying to like basically simulate some sort of like complex function by adding up these linear functions. And so they have these things called like activations, which essentially say like, I'm going to take a function and make it go like this, and basically just chop off anything under 0. That's one of the many functions. That one's called like rel_u. But now all of a sudden you can imagine that we'll say that there's other activation functions. The idea is that you want to be able to like disable the node in some way. And that way you can have like linear functions that kind of add up where if you have like, now you have this function and like this function and this function. And when you add those up, they now create something more complex, right? And so that's really like the only really core building blocks that we need. And then all you have to do is, as long as you have an output where you can like tell what inputs you used and how wrong you were, you can kind of like adjust the slopes and biases of these lines to try to like draw a graph that you want. So let's just try to like build up that concept of like neural network training from scratch here. And, or not from scratch, sorry. We'll just try to like build up the concept of like, what do we have to do to like train a neural network? And we'll start with something simple, I think. So this is talking about training a classifier. I don't really want to do that. I want to just train like, first let's start by training just like a linear function, right? If we have a function that is like, we have like f of x is equal to mx plus b. Let's say that we just define m and b to be certain numbers ourselves. So we'll say like m is like 4 and b is like 3. And if our understanding is correct and these nodes are, each of these nodes is like a linear function, we should be able to train this with a single node neural network. And so that's kind of like the simplest case I can think of. And so let's just try to build that and build off that and see where we get to. So, neural networks. So in Pytorch, you define these like networks of layers, they call them. Linear just means that you have an input that is connected like this, right? So like this is a linear layer with 2 inputs and 2 outputs. This is a linear input with like 2 inputs and like n outputs. We don't really know yet. So we should be able to like define a network, it looks like, with a single linear node with 1 input and 1 output. And that should be enough for us to define what we want to do. So let's inherit this guy. So another piece of information that's like really important with like Pytorch that I don't really like is that like you might think that if you understand the math that like you can take shortcuts and just type what you want. But there's a lot of like stuff going on under the hood in Pytorch. So you kind of have to like follow the way they do things for stuff to have expected behavior, I guess. We'll get into that a little more later, but just heads up there. So we're gonna import their like torch, and torch, I think NN probably stands for neural network. We'll make a class for a classifier, or not our classifier, our like network, and we'll just say that this guy inherits from NN module, like they say to. And we define some sort of constructor. And one of the things in here, or like our only thing, is going to be our layer is going to be a linear thing that has 1 input, 1 output. Boom. I think that that should be good enough. We define this like forward function, which is effectively saying like what happens when we try to use this network. And you can put anything in here, really. But what we're just going to say is we're just going to use that layer on our inputs. So I think that you could just say return self layer x. We'll get a little bit more into like what forward means in a minute. But for now, we're just going to say that that means like it's essentially like the call operator. What happens when I call my model? We call forward. Okay. So here they say that they're going to pull the parameters out of the network, which is kind of why we have this like NN module stuff. I think that there's some sort of like magic that's going on under the hood. So I'm kind of curious what that is. So let's say that we have our network, and it's our network that we just made. And right now it doesn't do anything. But if we were to like call a network with some inputs, it would probably give us some outputs. Probably. So we can say like, let's make a network and let's just call it with like a input of 2.0. I think that that's probably going to work. And let's just see what it prints out, if it does anything at all. Which it does not, because what is it bitching about? Cannot assign module before module init call. So I think we probably just forgot a, yeah. So we're inheriting from this like neural network module class, and so we just have to say, hey, could you please run any initialization code of my parent before doing stuff in my child? And you can already tell that like the fact that this is like throwing an assertion means that this guy must be doing something like fucking complex, right? Like this guy must be doing some sort of registration with the parent for it to even know that the parent hasn't been initialized, right? Okay, so we ran our like function. We said, hey, run the network with 2.0, and it gave us back a number 2.0. So theoretically, like 2.0667. So that means that it could be doing some sort of multiplication over there. It might be doing some addition. And so maybe we can like poke at it and see if we can understand it a little better. So I think that in that like demo or the site we're reading, there's something you can call network parameters. And like, what does that do? Oh, we have to iterate it maybe, turn it into a list because it said it's a generator. Do I call list on a generator to turn it into a list? I just want to like actually iterate the objects. Yeah, here we go. So this is a parameter containing a single thing, or maybe this looks like maybe two things with two values. I would like to like get a better idea of what that is. Maybe we can like jump to what this like parameters function is doing. Returns an iterator over module parameters. So for object in named parameters, returns an iterator over the module parameters, using both the name of the parameter as well as the parameter itself. So maybe we will throw a named parameters in here, and it might give us a better idea of what this thing is actually trying to do. It's a generator again, so maybe I have to turn this into a list again. Oh yeah, okay. So here, nice, perfect. So here we see that we have a member layer with a parameter weight inside with the value of this guy and a bias containing this guy. So we're getting the number negative 0.3659, and if we did like our input, which was, what did we punch in? I think it was 2 times this weight plus this bias. Do we get the same thing? And we do. Okay, so we have like a decent understanding of that. Like what we understood before we started is like correct, right? We have one layer, he's doing one multiplication and addition, and that's giving us our answer. Cool. And also interesting here is that like it's using the term layer here, which is what we named our thing. If we named our guy like ASDF, let's chmod plus xtrain and run train. He's now like renamed from layer to ASDF. So we can like already tell that there's like some like wacky shit going on under the hood here, right? Like you would not expect that by assigning a variable in your class that you would get like this like registration where you can like iterate over them, but it knows, which is going to be an important concept for later, right? When we try to like optimize this network when we're training it, the fact that it knows what all of our inputs are, or like what all of our module parameters are, will allow it to do the optimizations that it needs to do. Okay, so we have our network, and do they have just like the answer here? Yeah, here. Okay, this is mostly what I'm looking for. So the way neural network training works, is, what's like the easiest way to show this? Probably drawing a graph. Okay, say you have some complex function that you're trying to learn, right? It goes like, and you want to find like, how do I say this? You have a complex function, and you also have like a guess for each input, right? Like say that like we just randomly run stuff through our network and we get like this, right? What we can do is we can like subtract the correct answer from our guess, and we'll get some form of like this minus this is low, this is lower. So our like, if we subtract our guess here from like the actual answer, this will start to look like something more like this, right? And if we're essentially trying to say, hey, I want like my right answer or like my guessed answer minus the correct answer to be 0, right? Like that's what we're trying to do. We want no difference between what we guess and what we get and what the correct is. What we can say is like here, we want to adjust our guess to get closer to 0. And here we want to adjust our guess to get closer to 0. So here we want to make our guess come up higher, and here we want to make it go lower so that it matches the shape of this guy better. And you can do this by kind of saying like, well, how does our like inputs to our guess affect the answer? And you can use like calculus essentially to say like, which direction should I move? I guess, right? Because you can think of each of these like nodes in our network as another like a dimension in which you have like a thing to change, right? You have like function of like node 1 and node 2 and node 3 and node 4, as well as like input 1 and input 2, etc., right? Like whatever your inputs and your nodes are, that function is going to return something. And you can like kind of imagine that each of these inputs like is another axis where you can like change stuff. And these guys will affect the answer. So you can just kind of say like, hey, if I like graph all inputs here through my function, you'll have some sort of like n-dimensional like thing. Maybe I'll like in Blender, we can like just kind of like, I want like some sort of like 3D thing to look at to kind of visualize a little bit. So let me just quickly make one the only way I know how. So hold on. How do I do this again? I'm rusty. So like, let's say, one sec. One sec. We're just trying to make like a hill. So I can like noise and set position. And take this input and put it to this output, and then offset by some amount in X, Y, Z only. Yeah, okay, cool. This is what I'm looking for. Right, so say I have like some landscape, right? And say that like each axis here, like vertical is like the output of my function, and the Y and X axes are like parameter values, right? So if I'm trying to like get my difference between my output and what I guess to 0, you can imagine that it's like a minimization of some function. Like we're trying to get like the lowest value that we can possibly get. And like somewhere in this landscape of like inputs, there is like a lowest point, right? Like, but there's also like lots of almost lowest points that are almost as good. And so you can kind of imagine that if you were like hand wavy, and if you're like a ball, you know, you're at this point in space and you're like, which way should I go to get a better answer? You essentially just want to move down the hill into like the lower values. And hopefully when you get low enough, it's close enough that it's right. So all we're doing is we're like, at the end of like our neural network training, after we run our network on our input, we say, well, there's a right answer. How far are we from that? And then we basically do calculus to find out which way do I move to, like, what is the slopes of all of my dimensions, and how do I like set parameters to get closer to 0? And that's essentially all we're doing here. And that's like why this is like the training loop. You just say, run input, check how bad it is, optimize, do it again, baby. And that's it. That's really like all neural network training is. And so like Pytorch, what it's giving us is it's giving us a lot of like math and like tracking and GPU acceleration to essentially track all of the changes that you make when you run your network, right? Like when I run my network right now, our simple network that we're running is just one node that is one linear transformation. And it says like, oh, when you run that, you did this linear transformation. And so like, I know how much that affects the answer. And I can remember all of the like backwards how do I say this? Sorry. If you have like, 3 nodes in a row, you have like your answer here, you have your input here, and you can say like, well, how much did this affect my answer? And how much did this affect that? And how much did this affect that? And you kind of like adjust things along the way. And so that's why they call it like backward propagation, because you're like propagating backwards to figure out how much you need to change each of these things to make your answer trend in the direction that you want it to trend. Sorry, that's a really poor explanation. I would highly, highly recommend the Sebastian Log video. It's like about like an hour long if you want like a better understanding of that. He explains it much more eloquently than I can, but that's kind of like a good enough explanation for now, I think. Yeah, so that's all we're doing. All we want to do here is we want to say, well, we have like an input. So we're going to say we're going to do this train for some amount of time. So we'll put it in a loop. And we're going to say that we have an input, and maybe we have lots of inputs, right? We can do this for a lot of guys at once. So we'll say that we're going to generate some like random numbers. And maybe we're going to generate like, 4,000 of them. And I'd say 496 because I'm used to powers of 2. And these are all going to be in the range 0 to 1, I think. So we might want to like make them in a little bit of a larger range. So we might want to say like times 1,000 minus 500 or something. We'll call that inputs. Inputs. And if we print inputs.shape, we should see, let's see, we see an array of 4,096 values, each of them with 1 value inside. And the reason we split this up is so that the network, I'm pretty sure that you have to have a 2-dimensional thing for the network to know that it's running on more than 1 item at a time. And then we can just say like run the network on the inputs. So we'll say vals equal this. And I think we can just say loss is equal to, I guess, output is this. We have our like expected value is going to be our inputs times our slope 4 plus our offset b, right? Because we said we're just going to try to train this linear function. And I think that you can just do expected minus output and then loss backward to say, hey, run all of the stuff backwards to check how, like, do essentially this step here where you want to like calculate how much of an effect each of the inputs had on this loss, and then run our optimizer, which we haven't initialized yet. I'm not 100% sure if you need to do some like extra Pytorch bullshit for this loss to do what I want it to do, so I'm not 100% here. But let's just kind of try it and see what happens. And we need to import probably torch.optim. Don't say as optim. There we go. And I guess now we will print the loss and see, what we hopefully see here is that it goes down over time. It doesn't like that, so let's see. I fucked something up. Gradient can only be implicitly created for scalar outputs. So this is coming from our backwards pass. So maybe we need to do something a little bit more intelligent. They have like loss functions, so we'll just pull one of these out for now. MSE loss seems pretty reasonable, where MSE loss is just like mean squared error. So they take the error for each value and then they square it and they take the average, which makes sense here because here we have like a loss of like many values, right? Loss.shape. Right, so we have a loss that's 4,096 values, and they want the loss to be one number. So we could do something like probably just do sum of all these guys, and that would probably be good enough. Let's see. Yeah, okay, so that does something. Let's not break out of the loop and see if this number goes down over time. which it is, but our loss can be under 0, so we actually want it to be absolute valued probably. And now we're seeing not what I would expect. Well, it's hard to tell because it's moving so fast. Let's just print it out maybe every like 1,000 iterations. So we'll say I is equals 0, I plus equals 1, and if I percent 1,000 is equals 0, we print the loss. Oh, geez, we're still printing something else every time, though, so we'll delete that. Okay, so our loss is off the fucking charts. So there's a couple reasons that could be happening. One is that, I've always forget this, like, incredibly important step. So our optimizer, he basically decides, when I'm, like, moving this ball around on this hill, he's like, how far do I want to move it, essentially? Right? Because you can imagine if you're here and you want to move towards like this little valley over here. If you said, I'm going to move like 10 steps in that direction, you might end up like all the way over here. Versus if you said like, oh, I want to move like 1 step in that direction, you might like end up exactly where you want to be. So the optimizer like chooses how far to walk in a given direction. And an important step here is you need to like reset his state every time you start recalculating. Optimizer 0 grad. Otherwise, he will kind of like accumulate stuff over time that you don't want. So does that look any better? Are our numbers shrinking? Arguably, yes. Right, we can kind of see them like occasionally dropping a lot. It's possible that our learning rate is much too high if we're not seeing it approach 0, because I would expect it to get very close to 0, since we're trying to calculate a single linear function, which our one node should get to the answer very quickly. I'd be curious if we drop the learning rate even more. Do we see... Oh yeah, you can tell when we drop the learning rate, the numbers are getting way, way closer to 0. So let's just keep dropping it until it looks about right. Maybe not. Maybe not. We're still quite off. But it would be interesting to maybe also print out what happens when we run our network on something. So here, let's just run our network on like... I don't know. Let's just run it on like 1.0. And see what we get. He doesn't like that because I need to run it on a tensor. Pytorch tensor. Tensor. There we go. And I guess maybe this needs to be like with the shape -1, 1 or something. I don't know, man. I missed a closing bracket. There, he likes that better. So when I run on 1, we're seeing this guy steadily increasing, which is kind of maybe interesting. Maybe not. I don't know. Okay, let's try using like a proper loss instead of what we're doing. So let's try using mean squared error instead of our just like naive sum. So let's just pull this guy in. And let's see if we behave any better if our loss is criterion. What is this supposed to be? Do we say expected output and target? There we go. Let's try that. Okay, so that might be... We see like much more stable numbers there, which is interesting in terms of like our loss over time. And it could be now that we need to increase our learning rate now that we have a more reasonable loss. Immediately nans, which is an indication that like something's multiplying by something much too large and getting out of whack. Ah, there we go. Okay, so we are seeing the number trend down here, which is like a good sign that our network is learning. He's learning kind of slow, so maybe we can try bumping up our learning rate a little. Too much, we can assume if we're getting to nans. Okay, here we go. So he's like decreasing pretty rapidly, and maybe we'll like set some sort of threshold for what like a good answer is. Like, how do we decide when he's like good enough? Because in neural network land, you're only kind of like sampling the world and trying to fit a function to the samples you see. So he'll never be perfect, but he at some point he'll be good enough. And so we should probably set some sort of threshold for what good enough is, and stop him from training at that point. Let's say, well, first let's train him like a little faster. And let's then say that we'll stop training if loss is less than some amount. And this loss is actually, mean squared error. So he's averaging over the square of all errors. So yeah, something like 0.01 might be good enough. We break, maybe, well, what values we're going to use? We were approaching 0.01 there, so I think that's reasonable. And then at the end there, after we do all that, let's, I think that you put the network into, like, evaluation mode, I think, which says, like, hey, don't track shit anymore, I think. Not quite sure there, I don't remember, but I'm pretty sure, I remember seeing this in some cases. Then we can, like, run the network on some inputs, like 1.0, 2.0, 3.0, and 4.0. And let's print our results there, as well as print out the parameters of the network. And I think we saw before that we need to convert those into a list, because it's like a generator thing. Okay. So we immediately NAND, so this learning rate is too high. NAND again, interesting. I thought that maybe we were like right on the edge of where it's okay. Here we go. So we need to wait for him for a second to approach the value that we expect to approach. 0, I guess. We need to wait for him to get to our threshold, which should be hopefully soon. Give him a sec. I'm doing all training on CPU right now, which makes everything like a fuck ton slower, like orders and orders of magnitude slower. But it's because I don't really trust my GPU to not crash, and if my GPU crashes, then the whole stream dies, and that's a pain in the ass. So we're trying to see what we can get away with on the CPU, and then we will move on from there. Like maybe I'll like, fuck. He doesn't like that this is a one-dimensional tensor. Fuck me. So this tensor has to be shaped as a bunch of one-dimensional inputs. So let's just immediately break to make sure that that code doesn't crash us next time we do this, because we don't want to have to wait for that whole time again. And let's run her. I'll also note that which optimizer you choose has like a pretty major effect on training speed. So I think I've seen in the past, like this guy that we copy pasted, he's using SGD, but there are other ones, Torch optimizers, well, first let's find out what the fuck does SGD even mean. Implements stochastic gradient descent. Okay, so what's that? Stochastic gradient descent. Iterative method for optimizing objective function with suitable smoothness properties. It can be regarded as stochastic approximation of gradient descent optimization, where gradient descent is just walking down the hill, like we were talking about earlier, since it replaces the actual gradient by an estimate thereof. Okay. Let's see. Does anyone here tell me what's like good? I think I've seen Atom before. But I don't really know which is like best. Pytorch, good optimizer. This is how I learn. Which optimizer should I use? TLDR, find a related research paper and start with the same optimizer. Ugh. Great. Okay, so here's like some names of things. Atom, RMS prob, Adagrade, SGD. So We might want to try some of those out at some point. Okay. Okay, so this is kind of interesting. So we got to like some result, right? We got to our like loss, and our weight is 4, and our bias is 2.9. And we made a function where we said we want a linear function with a weight of 4 and a bias of 3. So what it like eventually came up with is like pretty close to what we asked for, and it just took them a while to get there, which is pretty sick, pretty neat. So I would consider that done, and maybe let's like try to like increase the complexity of our network a little bit. And so we could like say, well, say we don't want just like a linear function. What if we wanted to do something like approximate like a sine wave, maybe, right? We could say, instead of our expected being this, all we have to do is make our expected torch.sine inputs. And all other code, I think, can stay the same. But what we might find is that, like, since sine cannot be approximated well with a linear function, all of a sudden we're going to start getting, like, we're not going to get good enough, right? We're not improving. You can see that these numbers are kind of staying close to 0.5. So we need to start adding some complexity. And do we think that we can get away without any hidden layers? Or, sorry, with one hidden layer. So the idea is that we have one input. We might want to splat that out into, like, several linear functions, right? When we were talking about before, you have, like, if you add this function to, like, this function to, like, this function, you could imagine that you could, like, find some set of functions that works for the range, like, 0 to 2 pi for sine, that, like, approximates this, right? Is sine this one? I can't remember. If sine cosine, this is cosine, this is sine. I think that's right. So we want like something that approximates this. And so you could like probably approximate it with like 1, 2, 3, like 1, 2, 3 lines would be like kind of like a minimal shitty representation. So it'd be kind of interesting to see, well, if we started with 3 lines as our like first thing that we do, linear 1, linear 2, and then we like somehow combine those 3 lines back into a single output. What do we get? But the trick here is that these guys also need to go through activations. So I think there's called nerual. Yeah, that looks right. And I don't know if these guys have, like, trainable parameters. What is this? I'm pretty sure that a rectified linear just says, like, hey, cut me off at 0. Which sounds like that there's no, like, trainable parameters in there, really. And so making, like, parameters in the network might not make sense. Like, we might just say, I think that they have, like, functional versions of these parameters that you can just like, call functions. And then you say, what? We call x is self linear 1 x. X is equal to functional rel u x. So we do our, like, activation, and then we do call the second linear thing on the output. And hopefully that's, like, enough to give us, like, a very shitty sine approximation. We want our inputs to be in the range 0 to 2 pi, so we'll just say multiply by 3.14059 times 2, I guess. And we'll see what we get. We'll see what we get. We'll see if we get, like, something that approximates it at least a little bit. Oopsies. Yo, what's up? How am I doing? We're doing good. We are trying to learn about neural networks. And here we're seeing, like, some decrease, which is good, down to a loss that's lower than what we had before, right? Before we had our loss hovering at 5 with one node. But here it seems to be decreasing. It looks like it's, like, kind of... Oh, maybe it's still decreasing. It'd be interesting to be able to like pause, like to just break out the training whenever I feel like, or maybe press a button to like print out this stuff. So maybe we can say like if, can we like Python check for input? User data. No, I want to check for keyboard input. I just want to like press a button and see if it hits. Import Py input? No, there's got to be a fucking way for me to do it without an external library. Am I crazy? There's got to be Python user input keyboard. Yeah, there's like an input function. Here we go. And does this input function have like a timeout? Python input timeout. You're going blind because of the light theme? Dude, people hate light themes for sure. Jesus, is it really not possible to just like optionally wait for an input? That's crazy. Timer, input prompt. Dude, that's wild. I guess it's because they don't have threading. Well, that kind of sucks. I guess I'll just print this stuff every thousand iterations or something. For now. Might need an extra activation function after the last layer, though, in order to further restrict your values. One suitable for the task might be sigmoid. Yeah, maybe. We'll see. The only reason for a light theme is when you sit outside in nature and do stuff where the evil laser starts to blind your monitor. Okay, hold on. Okay, hold on. I've never understood this, like, light theme hate. So, like, let's look up, like, bright, like, what's the, like, there's a metric for how bright things are, and I'm blanking on what it is. I used it a lot when I was working with cameras. Unit for how bright stuff is. Luminance? Is that lumen? Yeah, okay. So like, can we look at like the lumen of like the fucking sun when you're outside versus like inside and looking at a monitor? A monitor's so fucking dark. Like, brightness, relative brightness, inside, outside, Wikipedia. Oh, God, I'm fucking blanking on, like, the correct... Like, I've seen this, like, chart before that's, like, the sun is, like, thousands of times more bright when you're sitting outside. Lumen, sun, light bulb. Like, the sun. I'm blanking. But it's, like, I've never understood the hate on, like, monitor brightness, because it's like it's fine, like the white light versus the sun. Nobody stares directly at the sun though, but just like daylight in general, like just having your window open is so much fucking brighter than a monitor, but like you just like adjust. I don't know, man. I don't know, I've never thought it's that bad, but people hate it, so maybe I should use dark theme on my browser just so that my viewers don't hate me. Are you talking about Paramount Engine? That's not what I'm... Maybe I'm thinking of Lux. Yeah, this is probably... This sounds... Here we go, yeah. Overcast day, full daylight, you're looking at like 10,000 to 25,000. And like in like an office building lighting, you're at like 80. So it's like... Is this like a logarithmic scale? Anyways, it doesn't matter. You're right. Think of the viewer's eyes. Fine. I'll consider it. I want my like things that I'm showing here when I'm trying to approximate sine function. It would be interesting to maybe like graph it. Can we do that? Can we show like a graph over time? Right, we could try like running... We could try running, like, a bunch of values in the range of 0 to 2 pi. And then shove them in a plot or like a CSV at least. Let's do that. Let's dump them into a CSV and then just like open it and graph it in Excel. That seems most reasonable. So we'll open a file and how do you like open with open output CSV with like write as F. This is like the Python way, I think. We take a bunch of numbers and we want to try like, we basically want like even steps in the range 0 to 2 pi. So I think there's like some way for me to like generate a tensor with like monotonically incrementing values. Torch. Do I want to open the file in the learning loop every time? Fuck it. Yeah, every like couple thousand iterations. Later in the future, we'll build like some sort of better visualization for what we're actually working on. But for now, I think that's like good enough. There's like torch incrementing numbers. Form a sequence of torch arrange. That's what I'm looking for. So we'll make like maybe like start number, end number. I think these are going to be in integers. So we'll start by making these like, we'll just say we're going to do like 500 samples. And then we'll divide these by 3.14159 divided by 2. And we should say then that we have like our values. Or we'll say like our inputs. Outputs, we will just say that these are our network run on our inputs. And, oh, this guy, I guess, also has to be reshaped to be two-dimensional. So we'll just say, I don't care how many, but each one will have one element inside. Outputs. And then we will just say, I guess we want to like iterate over all these guys, which I'm not really sure how to do. I think it's like, I think you can just stick these guys together, or for I in len inputs, I guess we'll just do f.write input output inputs I outputs I0, maybe? I'm not really sure if this works, but we'll see. We will see. I don't really know how much these things act like arrays, or I don't know if I have to do like an intentional transfer here somewhere. Int object is not iterable. That makes sense. So this is range inputs. And he doesn't like that I gave him 3 arguments because I was supposed to say this dot format these guys. That's the Python way of doing like your printf style strings, I guess. Okay, so do I have a CSV, output CSV? And I have to write new lines. Oops. Oops, oops, oops. So here we'll write a little \n. And can I like cat output CSV? Okay, so my inputs are going from like 0 to 7, like way higher than I thought they would go. Oh, because I'm not supposed to divide this by 2 pi. I'm supposed to divide this by 500, then multiply this by 2 times pi. That should give me values in the range of what I'm looking for. There we go. So those are values in the range 0 to 2 pi. And I guess we also want to print our loss here. So that we can see like approximately if we're like in a good spot. Okay. I guess let's just graph these guys. So I think what's like the best way for me to like quickly graph a CSV? Like LibreOffice Calc. LibreOffice is probably what I'm supposed to download here. It does look like it's still, it looks like it's kind of like stabilizing, maybe still moving down a little bit. But let's see what we approximated with our 3 lines. Come on, buddy. You can do it. Okay, so LibreOffice output CSV, and this should open up LibreOffice Calc, I think. Yeah, nice. And we can probably just say, like, please graph these guys. There's, like, a graph button somewhere. This guy, maybe? Nope. This guy, maybe? And we want, like, a line chart. Column A, column B. That's not what we wanted. Fuck. We want column A to be our axis. Or our, like, X values. It's been a while. It's been a while. So I want XY scatter, maybe. Yeah, that's like looking what we want. And we can see that that isn't at all what we want to see from a sine wave. We do see like a kink in the line here. But it does not look very good. Loss is still going down, so it'll be interesting to see how this compares over time. So can we can we like reload this file? Reload. Okay. What did I just do? Here, I opened a new one by mistake. So let's see if this is any better. Graph. XY scatter. Not looking any better. So it looks like our network is like not good enough. Is basically what we're seeing. And you can tell pretty obviously by looking at these numbers that like scrolling down, it's just not good enough. So somebody suggested that we might need an activation at the end. So let's see if that changes anything. Right, you can imagine that like we need to more intelligently combine our functions. Or there's a chance that we might need another layer or something. It could be that like my guess of like 3 lines is not good enough. Maybe we need more lines to approximate the function better. Also, I don't like how slow this is learning. I wonder if like, can we bump up the learning rate and have it not crash on us? Let's see. It looks like by bumping it up, I've removed its ability to learn. So let's try bumping it up a little bit, but not a lot. Okay, let's see. God, it's so slow. I did want to try also switching to a different optimizer and seeing if that changes behavior at all. Quite low. Let's decrease learning rate a little bit. I don't know if there's like a more scientific way to do this kind of stuff, but I do feel like when I've worked with this stuff before, a lot of times it is just kind of like tweaking parameters and seeing what works and what doesn't. That's interesting. I reduced the learning rate more and ended up with a more wrong result. I wonder if it's because, like, I guess maybe it's because, like, it's not learning at all anymore. How do we want to do like this? Can we print the loss more often? So here we're basically fluctuating between 2 values. I wonder, it's also possible like that our network is just not good enough. So maybe we'll just try introducing something in the middle just to like get a feel for if we're kind of limited by our network's capacity, and then we can try backing off to get our like shittier approximation later. So we've added like another 5 nodes in the middle, and we'll just see if that allows us to approximate our function a little better. And we need to undo all of our like optimizer changes. So we were using SGD, and our learning rate was like something like this. I don't know, it was somewhere around there. And let's not print the loss on every iteration anymore. Maybe the file handling is a problem for the speed. I guess that's possible, yeah. It's not impossible. It could be that like every 5,000 we're slowing down a lot. Okay, we do see the number going down. Maybe not by a ton. And let's maybe reload this and see if this looks any better. I feel like we are still seeing just a strictly decreasing value, which is not what we expect to see for a sine wave. Let's double check. I just want to double check my loss here. So we have our input is this guy over 2. We run torch.sine input, and maybe we should print the expected for this as well. That way, when we, like, just to make sure that I'm not doing like something fucking stupid. So we can say torch.sine inputs, and we'll just put the expected value here as well, just to make sure. So here we can say expected I0. And hopefully we'll get a feel for if our index or thing is shit or not. He doesn't like that for some reason. Invalid index of a 0-dimensional tensor. Oh, because I didn't do reshape. Sure. Sure. Okay, so if I reload this CSV now, we do see that he should increase then decrease, which we are definitely not seeing in our calculated thing. I feel like this should be able to train way faster. I do feel like that a little bit. I'm going to go back to... So we have a linear thing, another linear thing, a ReLU, and I'm going to play with these optimizer parameters a little bit more again, because I swear I've seen it converge much faster than this before for something very similar. And yeah, let's try disabling this like file reading stuff just to see if it goes much faster. 1 Mississippi, 2 Mississippi. Okay. Increase learning rate. Let's see. Oh, there. That number's way fucking smaller. Oh, okay, yeah, okay. I increased the learning rate and it just fucking, like, destroyed there. So let's remove this guy. So I switched to a different optimizer, increased the learning rate, and I saw, like, way faster convergence. Yeah, that's sick. Okay. So let's re-enable the, like, CSV output and see what we get. Give it a sec. Boom. Oh. That's interesting. So I think that what's happening is that by writing this stuff, it's actually affecting my results. So I think that that's probably what this net eval is for, and net train. To like say, hey, please don't like consider this stuff as like part of my actual training. I think. Maybe. It's interesting that like I see if I just like continue here, instead of trying to run the model on all that stuff in the middle, I see it converge so much faster. Which means that there's like some sort of like tracking going on that I think. Pytorch eval. We'll just search this and see what this does. Model eval, some sort of switch for specific players, parts of the model behave differently during blah, blah, blah. In addition to the common practice of evaluation is by using torch no grad. Oh, so he's like still computing gradients or something. And if I say like with torch no grad, I'll say like, hey, I actually don't give a fuck about gradients right now. And maybe that will do it. Let's see. Okay, so that looks like a nice small numbers like we wanted to see, which is sick. So I must have... How do you train if you turn off your gradients? I only turn off the gradients while I'm, like, checking the current state. When I'm writing out my, like, CSV of all the values. Sorry, so this wasn't clear. So here is, like, where I'm, like, actually trying to train. And then here I'm saying, like, every 5,000 iterations, let's, like, check on some, like, random shit. And I want to say, like, don't change my state by doing that. And so I'm, like, putting in the eval mode and turning off gradients. Not quite sure exactly what that means yet. I'll probably do some reading on that later. But when this section is exited, the gradients are turned back on. And it does look like it's doing something sane now. So let's pop back open our LibreOffice. And when the value gets like kind of small, let's reload and see if it looks a little better. Reload. And yeah, they're tracking a lot better. So we can now go back. We can look at the graph here of an XY scatter. And blue is like a shitty approximation of the actual sine wave, which is pretty cool. Pretty cool. And now I wanted to see if we like heavily reduce. Let's just like try with 3 lines in here. I wanted to see if this gives like a reasonable approximation, or the approximation that we would expect that you get with 3 lines, right? I would expect to see something that looks like this if we only give it 3 parameters, 3 linear parameters. Funny to see that the first part is a better approximation than the 2 parts of the wave. It's possible as well that like I have to double check that my training data, right, it might be only accurate where the training data is, and I'm not sure if I'm covering the right range with that. So we will have to double check that as well. But let's see, what if we reload this now? We do see something that looks like it might track to a little bit. Let's see. Graph. XY scatter. Okay, so that's getting close. We have definitely like 2 segments, but you can see like the second segment here. Like the third segment is almost like not coming into play at all, right? We don't see that anywhere, which is kind of interesting. We might be hitting like some local minimum where it optimized 2 of the parameters, and the third one, it like just started in such a shitty spot that it couldn't find out kind of how to hook it up. Or maybe it just needed more training time. Maybe. So can we like reload and see if it gets better over time? Graph? XY scatter? No, so he's just like stabilized on this like 2 parameter thing. And I guess we could probably how can we like look at this a little closer? So my inputs are, can we like print in max inputs and min inputs? We have to make sure that we're like evaluating the same space. So he's going from like 0 to 6, so he's training on the right stuff. But maybe we're just getting like, it could just be like unlucky, essentially. Maybe we'll give it like a couple more parameters to play with. We'll say, hey, you have 5 lines, and maybe it will use 3 of the 5 lines and give us what we want. It's also possible that I have to like initialize these guys. I'm not remembering quite right. And it's also possible that our optimizer parameters might have to change with the size of the network, which might be interesting. So we could like try decreasing the learning rate because we have less things to optimize and see if that changes anything. Would a dropout layer help? What's a dropout layer? Dropout layer are used in the construction of neural networks to prevent overfitting. In this process, individual nodes are excluded in various training runs using a probability slider. I think... Oh, you're right. That does seem like it could help. No, maybe not. I think that I would want all of... In my scenario where we have 3 nodes, and we're trying to get those 3 nodes to match a sine wave, dropping one of the 3 would result in like a guaranteed fucked result, right? So I think probably not, because you want like... I think that that's supposed to... My intuition here, having just learned about them 2 seconds ago, is that you would use these to make sure that you have like duplication in like noticing patterns, right? You might have like, if you, I would imagine like you're like doing some image detection and like you want to see edges. You want to make sure that like one node is not the only guy who's doing edge detection. You might want like two for like duplication of some sort. But that's just like my guess because I learned about this 2 seconds ago. So what the fuck do I know? Okay, let's try reloading with these like five items. Yeah, using it for generalize. I use it in text generation or text classification to make it generalize better. That makes a lot of sense to me. I can see that working. My fucking LibreOffice feels fucking frozen. That's really cool. Love that. Let's try opening again. Fuck recovering. Do you want to discard? Yeah, I want to discard. I've never clicked that recovery button, and I don't know if it's shit. But I've never wanted to. Okay, so that's better, right? We can see, like, we've got 1, 2, 3, 4 line segments. But the fourth one is shit. But I think that, like, we've kind of, like, proven to some extent that, like, it's working almost the way that we want. What's your loss function here? I've just taken, like, a bunch of random inputs and then calculated a sine wave for the expected values. And then I'm using mean squared error loss as the loss, but not really sure if that's the best one. It's just one that makes sense to me because, like, mean squared error. It seems like it would, like, penalize being really far a lot and keep everything positive. I think that, yeah, I'm not really sure. My statistics is also pretty bad. I just picked one and clicked the button and said, go now, please. Okay. I am curious can I get out of this? Reload. Is it getting better over time? It'd be interesting to, like, figure out how to get it to kick itself out of this, like, local minimum state. It's also interesting. I'm seeing 1, 2, 3, 4 segments, even though I have five inputs. Let's print out our parameters as well every time we get here. So let's say that we're gonna print network dot named parameters. And can I actually turn this into, like, a dict? That would be cool. I'd prefer that to turning into a list like we were before. Yeah, so we have the first thing is containing 1, 2, 3, 4, 5 weights, and 1, 2, 3, 4, 5 biases. And then and then we have 1 bias and 5 weights for the second one. So maybe the second layer isn't actually what I want. Hand wavy, if we're saying that we just want to add up the 5 line segments, this second one multiplying these weights is actually maybe overcomplicating things. The 4 isn't chaining. Isn't changing. Is maybe what you're saying. You're saying, like, the fourth indexed weight was not changing in this last one? I think I was seeing all of these. Negative 7724. Yeah, you're right. This guy's never changing, which is kind of interesting. That's so fucked. But that's matching up with what we were seeing. So it could be that, like, maybe that... Oh, let's see what's happening here. So here he's changing the weights. And are they all changing? No, in these ones, 2 of them have stayed very stable. But I wonder if the ones that are stable are the correct ones. Right? Like, these guys might have fit very well to some part of the curve. And so they're just like, all right, fuck it. We'll stay there. Yeah, maybe. It would also maybe be interesting. Let's try, like, increasing and or decreasing the learning rate. Right? Say we increase it a lot. Do we see our loss 0.7? Where here we had, like, 0.2. That's a lot better than what we had a second ago, but it's going up. So maybe, like, going up is almost certainly an indication that learning rate is too high, I would think. So maybe it was good where it was. So this is 0.2. Still going up. which is not good at all. Not good at all. Oh, wait, unless this one's the loss up here, which it probably is. We should print with actual helpful words in there. So we'll call it loss here. We'll call this params here. And is there another print anywhere? Okay, let's try that again. Aha, okay, so loss 0.8, 0.7, 0.5. And can we get better by like increasing this? Because I'm also hoping that if we increase it, we might get out of some of these like local minimums. 0.2, 0.17, 0.17, 0.16. So that's still decreasing. Can we like increase our loss even more? Or our learning rate even more? Oh yeah, look at that. He's tiny now. 0.0054. What does that look like if we graph this guy? Reload. Graph him. Scatter. Oh, look at that! Look at that! 3 lines almost perfectly tracking. But this is with 5 parameters. So I wonder if we could still get the same behavior with 3. That'd be kind of cool. So here our loss is 0.15, 0.15, but it is still like changing. I wonder if we like leave it for a little bit. No, he seems like he's kind of stabilized there. And what do we see? See there. Let's graph this. Oopsies, what the fuck? Graph? XY scatter? Oh, it's because I canceled. So it's possible that maybe you need a little bit more capacity than you would like initially guess, right? We think that we should be able to approximate our sine wave with 3 lines, which we saw, but it's possible that I guess like some parameters just get unused because maybe they don't start in a place that's like reasonable, or maybe if we trained for a really long time, we would start to see them learn better, or maybe you need to like adjust your learning rate. Maybe you need to start with a really high learning rate to get everybody into like somewhere reasonable and then like drop it over time. There's a lot of reasons why that might not work. But we did see that if we added a couple more layers, we did see like this like linear stitching of things together, which kind of gave us what we want. Okay. And so I guess let's try like doing like 20 of them, right? If we do like 20 segments, surely we'll get a more accurate result than if we did 5 segments. Surely, right? And so where is our loss here is 0.004. Loss here is 0.0005. 0.004. So surely this is like starting to look pretty good. Surely. And so let's see if we had 20 segments here. And here you can see like, yeah, that's tracking a lot better. It's still not perfect, but better. Yeah, that's pretty cool. Pretty cool. I've also noticed that a lot of our values, it seems like it's always good on like the top side and always shit on the bottom side. So I wonder if there's some sort of like bad bias. Like maybe our weights are starting in a shitty spot. It's all interesting that you always seems to allocate more resolution towards 0 than 2 pi. That's so funny. There's like 2 people in chat and me like all had like the same thought at the same time. It's like, why is it always shit on the right? Why is it always shit on the right? And I think that we could like check our like distribution of input values. Are your weights initialized randomly or at the same values? They must not be. I think I've seen people intentionally initialize with random weights. Initialize weights Pytorch. And I think I'm just not doing that. How do I initialize my weights in Pytorch? To initialize weights of a single layer, or a custom init module, we apply init weights. Yeah, fuck it. Maybe shuffle the sine wave inputs. But when we're training, they should be completely random, I think, right? when we are training, we do inputs, give me 4,000 random numbers in the range of 0 to 2 pi. We confirmed that when we checked the min and max of those, we got those right. So I don't think that there should be any like bias towards the later ones. The only time that we're doing them in order is when we are working with like our evaluation of those things. Is if you're not learning plus you have a small learning rate, that's just you're getting stuck in local minimum that end up with this like greater resolution near 0. But I would think that greater resolution near 0, does that not, is that for how to say this? Oh, you're right. Yeah, because like I guess as numbers get bigger, weights get more meaningful, theoretically. I guess, but I would think that like biases would offset that, but there's only biases applied after the first multiplication. Aha! Yeah. That seems like pretty reasonable then. So since that we don't have like biases before, the bigger the number is, just the less accurate it's going to get. So what we could try is we could try subtracting pi here. And I don't know why I'm typing out pi manually every time. Let's just import math and use that here. So we'll say times 2 pi minus pi. Yeah. I think ideally you want multiple runs with randomized weights and then choose the one with the lowest loss. I'd start randomizing the weights and see what it looks like. That seems reasonable. Yeah. I do want to try doing this negative pi to pi first though and seeing if that changes what we see. So we had here times 2 pi, and then we just have to subtract math.pi. There we go. Okay. Let's see if that looks any better. Loss sensor. So my loss already looks lower. I'm seeing like ease in here, which means that like we've passed where we can cleanly express with normal decimal values. I think ideally you run multiple runs with randomized weights and choose the one with the lowest loss. Yeah, that seems pretty reasonable. Maybe I already read that. I can't remember. I mean, I think there are actually big dick IQ strats with statistic dynamic learning rates to explore better solution space, but I don't know shit about ML. I think that I also have heard similar things to that. All right. Let's draw our graph again. XY scatter. Oh, look at that. Yeah, that's a lot better. Okay, so that's pretty interesting. But yeah, I think I'm happy with that. I guess, we wanted to try randomizing the weights. We wanted to, yeah. Oh, and while we're here, let's try reducing our number of steps back down to 3. Because if it's true that like the third one was always shit, maybe now that our values are like normalized near 0, maybe it will get the third curve okay. And we can tell that like the loss here is getting pretty small, even with the 3 weights. So there's some promise there for sure. Reload. Oh, wait, 3 isn't enough now. Now we need 4, actually. So we'll see what we get with the 3, because we don't have like that. The values are like normalized, or fuck off, LibreOffice. God, I hate software. I know all I do is write software, and this is a coding channel about writing software, but fuck do I hate it, man. It's like, and I'm not like saying like, fuck you LibreOffice developers, they're doing their best. It's just annoying. Oh no, yeah, that is 3 sections. 1, 2, 3. Look at that. We finally got there. We had a thought. 3 linear functions, approximate sine. Boom. There he goes, baby. That's sick. That's super sick. Okay, so that's like an interesting intuition that I've like never built up because I've never done this experiment before. But that's pretty good to keep in mind. I have heard before that like keeping values near 0 has like good effects. But yeah, that's pretty cool. Pretty cool. I especially hate NixOS because it's sort of that I have to do anything non-trivial, but every time it's such a pain in the ass. Yeah, dude, I've been there. I've been there for sure. And this like you're like trying to like remember this programming language and like how all libraries interact. But I don't know if it's like Nix's fault or just like coding as a whole, right? You're like, just the fact that like they're doing something like they're saying like, I want to track your dependencies. And just like build systems in general fucking blow. And NixOS is just like only build systems. So it's like, yeah, it is what it is. I think I learned more in the last hour than a month ago trying around by myself. Well, appreciate that. That's good to hear. Glad to hear it. Yeah, we're doing our best. Okay, so we're at 125. I was going to say that I think that like I'm kind of like happy with, I'm not happy. I've done this twice now. We wanted to initialize the weights randomly and see if that affects things. Let's do that. Okay, so we wanted to say, okay, so we know that like we behave better if we're around 0 to 2 pi, but we're also like, maybe our initialized weights aren't in a good state. So first let's print out what those initial states are. So we'll say print network.named parameters as a dictionary. And return early. I don't actually want to run the training. I just want to see what happens. So if I run these multiple times, it does look like it is initializing them not like consistently, right? We run several times. We're getting different numbers in here for our weights and biases. But I don't know like what their like default state is. Like when I create a network, like a linear section, what does it fucking do? Is there somewhere in here where it calls rand? Attributes, weight, blah blah blah. It doesn't really say. It doesn't really tell me what like the default values is. It could just be like random fucking memory, right? It could be just like I allocated memory and I didn't initialize it. Is there a way to make this plot automatically? Certainly there is, right? But we haven't. I think probably what I've seen before is people use like matplotlib in Python to generate the plot, and then you can just like hot reload the image that comes out. But I think eventually what I want to do is I will eventually probably write like a little web UI to do some visualizations. Would it be more comfortable to do this in a notebook? I would. There's probably a reason that every single AI developer I talk to uses a notebook, but I don't like them personally. They feel like there's like so much state baked into those guys, and like it feels like you don't have like a clean program at the end. I don't know, there's something about them that feels like to me notebooks feel error prone, but I can't articulate why, and there might not be a real reason why. It might just be like this gut feel that I have. But yeah, I think that I can totally see how like as someone who's doing data science and just like wanting to try stuff, there's a lot of like they let you move quickly at the very least. I think you're being way too generous. The reason AI people do anything is because they have stuff they have momentum and they hop on the momentum train. That's the only reason Python is popular. I think that you're right. There's a lot of momentum. Like for sure, the reason everybody uses Python for network training is because everyone uses Python for network training. But I also don't think that Python is like a bad choice, right? Right, like when you're thinking about like what you're doing when you're like running neural networks is like, or sorry, when you're like running like Torch, right? You're kind of like doing a lot of like GPU things, like GPU actions, and you're trying to like stitch them together. And I would argue that Python's actually a really good language for stitching together C modules, right? Like if you're like, I have a C module that does this operation fast and I want to like do that, then something else. Python's like a very flexible way to do that, especially if you're not like really good at programming, or if you're just trying to move quickly without like the concept of error handling or whatever. You think it's so bad? I mean, I worked in Python for 2 years and I still don't really like it. So I can see where you're coming from for sure. I just think it's like, it's not the word. If your goal is less about programming and more about finding out answers, I would say that Python kind of lets you do that. I don't think that I would ever try to write like a large piece of maintainable code in Python. But if you're just trying to like stitch together different libraries and like move quick, I feel it's good. Yeah, okay. You're kind of saying the same thing I'm saying in these last two. You see Python as a scripting language, a hacky way to do things quickly. But if you want to make a mature software project, Python is a terrible choice. Yeah, I agree. The main good thing about Python is a significant white space. I will never agree with that, ever. Hell no. Significant white space? No way, man. No way. What was I trying to find out? I got distracted. I was trying to figure if the weights are randomized in some way. So these are like made by parameters. And when they make new parameters, they make an empty thing. Oh, that's if 0. They make a subclass of a tensor, okay, which is some C++ thing. So I wouldn't be shocked if it's just like, I would not be shocked at all if this is just like random fucking memory. Let's see if there's like, can I Google this? Are torch parameters automatically randomized? Yeah, this doesn't really say, doesn't say if there's any auto initialization. Blah, 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 variables, parameters, blah, blah, blah. This isn't really what I'm looking for. I just want to know like if they're automatically randomized. Torch parameter automatic initialization. Torch and then init. All the functions of this module, blah, blah, blah. Okay, so maybe you're supposed to use some sort of, this is like, these are just like functions I can call. But I just want to know like what happens when I make a parameter. When a module is created, its learnable parameters are initialized according to a default initialization scheme associated with the module type. Aha! For example, the weight parameter of the linear module is initialized from a uniform, blah, blah, blah. Okay, so this is what I wanted. How the fuck am I supposed to find that out? Other than from this like tutorial. Oh, man. Not like I try to remember, as someone who writes open source code, I should never get mad at somebody who provides open source code to me, because I'm of the opinion that if somebody puts their code on the internet for me to use, like, they don't owe me jack shit. But it's, man, I wish I knew. I just wish that it was easier to find this info. Like, I wish I knew how to get it. But it's not their fault, it's mine. The most unbelievable thing to me is that Python REPL doesn't have a simple short command to reload the loaded files. Like, what the fuck is that? I mean, I guess hot reloading is kind of like a semi-advanced feature. But yeah, I've wanted that a lot of times too. Okay. So all of that, we got distracted a little bit, but we do now know that the weights and biases are automatically initialized with -1 over square root to 1 over square root distribution. That's a weird distribution, but I'm sure that there's some sort of statistical reason to do that. So I guess that means that I shouldn't expect things to improve if I automatically randomize them. So I'm kind of okay for now with like the idea that we should stay close to 0 at the very least for the first layer. That seems reasonable to me, because like we can't offset things with a bias later, or like right off rip. So okay. Yeah, okay, so what I wanted to do after this, after we got like some neural network working, is I wanted to start defining like what our inputs and outputs are going to be for our network that's going to do this, right? But I think that with like half an hour, if we're like 1.5 hours into stream, certainly turning, like if it took us this long to get to like a sine wave, it will certainly take us longer to get to image to text. So I think it probably makes sense to like call it there and pick that up as like the starting topic for tomorrow. So thank you for watching, everybody. If you liked what you saw, I'm gonna come back tomorrow and continue this project at around 1 or 2 o'clock Pacific time. I stream most days at around 1 or 2 o'clock Pacific. And if you miss a stream and you want to catch up, there's a VOD channel on YouTube that's like linked in the Twitch description. And if you're watching on YouTube and you're frustrated by my complete lack of AI knowledge, you could come in here and tell me why I'm wrong. There's a Twitch link in the YouTube description. And I stream every day, 1 or 2 o'clock Pacific time. So yeah, appreciate that. Appreciate y'all. Catch you on the next one. Bye.